Alright, we're going to look at Ohm's Law in this video. Set my computer, my notes here. So we're going to do some work on the board. You'll probably want a calculator and pencil out, pen, paper. There we go. So you can do some practice problems with me. I'll grab my calculator too. Okay. Got it. Okay. So, Ohm's Law. Ohm's Law. Ohm's Law is a way to look at the current, voltage, and resistance in a wire for electricity to flow. So this relationship has an equation associated with it. Its current is voltage divided by resistance. If you're one of those people that like the triangles, we can put it into a triangle to make things a little easier for you. So we have I, V, R. Keep in mind, when you're using this triangle, if you're searching for something like resistance, you just cover up resistance, and then you have voltage divided by current. So if we're going top to bottom, we're dividing, and for like next to each other, we're multiplying. Let's draw another triangle with our explaining what that one really is, because that's not super clear to me either. Just trying to make it big enough that we can see in there. Okay. I'm going to write their names in there on this one. So we have voltage. That's measured in volts. See how they're naming that one? Real tough. This is resistance. R for resistance, not too difficult. It has a great unit. It's called, oh, that is a bad drawing. It is called the ohm, which is why we have Ohm's Law. It's named after somebody else. So they use the Greek omega symbol. Kind of looks like a circle that's not connected on the bottom with two lines coming off of it. Hopefully that's big enough for you to see. Not in a glare. What's our last one? Oh, I. Current. So we have I. No, I don't want I want current. And that was amps. Again, named for somebody else, Ampere, but some French guy. And let's define these pieces here too. Again, in the previous video we talked about a lot of this stuff. So this is voltage. Was it electric pressure? How much those electrons are being pushed to move, right? This was electrical flow. Kind of grew into one word, right? Like a river, right? How much that's able to go. I can't define it without using the term. This is resistance to flow. So remember we talked about like rivers. Big rivers can allow more electricity to flow. If you have more electrons pushed together in a battery, they're going to have a bigger electrical pressure, more voltage, try to jump out. This resistance to flow is a new one for us. Just trying to find something real fast. there it is. So there's a few ways we can create resistance. One, which wire do you think it's easier for electricity to flow through? The big one or the little one? If I'm trying to send a ton of electricity through the big wire or the little wire, which one's going to have the easier time to flow? The big one, right? Think about the hallway. You're the electrons in that big hallway. If there's no one else in there, how hard is it for you to walk down that hallway? Depends what class you're going to, right? But let's say that hallway's packed full of people in a non-COVID year, so it's packed in there and nobody really wants to move, right? It's harder to move. Or we could shrink down that hallway, make it more narrow. With all those people in there, harder to move still, right? So the hallway width normal, right? Then we shrink down the size of that hallway, make it 2 people wide. How hard would it be to move? Normal hallway, narrow hallway, normal, narrow, right? So that's one way we create resistance, is a thinner wire, or reduce resistance. The other way is this thing called a resistor. I'm going to hold one up. Hopefully you can see it. It's just a little piece of ceramic, I think it's ceramic, and there's some wires wrapped around in there to reduce the flow of electricity. So it creates resistance by its design. Again, probably more above our class than what we need. Another way to create resistance, this is an LED bulb. They're not great for resistance, but if we go through a light bulb, we're met with some resistance, which is how light bulbs work, because we're heating up, and we mostly have fluorescent tubes now in like the school. In that case, we're heating up the gases in there because we're having electrons jump through them, and because it's harder for them to jump through those the gases in the tube, they're glowing. The old light bulbs with a filament in them, little thin piece of wire. It heated up and glowed because it was full of resistance. So those electrons were struggling to get through that thin wire, heating it up and glowing. That's how your toaster actually works, is it creates some resistance for the electricity to flow through the little heating elements, and those little pieces heat up and then toast your toast. But that's what resistance is just making it harder for electrons to flow. A lot of this can be used to calculate how much electricity we need to send through a house onto something. Like you don't obviously want to send a ton of electricity through a light bulb, it's going to burn out. These LEDs don't handle a lot. We can burn them out really quickly and easily, which is why when I wired this up I put a resistor in there so it doesn't burn it out. But we want to control how much the electrical flow is and how much pressure there is, so we can use resistors to do that. So we're going to try some practice problems with this. I'm going to get rid of this piece here because you can always go back and rewatch some pieces and catch some stuff you missed. So I'm just going to go straight to your assignment and do some of those. We're going to start here. It says a 9-volt battery is connected to a small light bulb with a resistance of 3.5 ohms. It's got the omega symbol. I'm on number 3. What's the current in the bulb? So I want to figure out the current, I. I'm going to cover up I. I equals voltage divided by resistance. There's my formula. Now I just have to plug things in. What's my voltage given? It's a 1.5 volt battery. So 1.5 volts. What's our resistance? 3.5 ohms. So we put ohms. I should do it this way and then just, there we go. That's a pretty decent omega. And now we're finding current still. So we're just going to take our calculator and go 1.5 divided by 3.5, giving us 4.3, or 0.43, sorry, 0.43. What was our unit for current? Amps. I believe we use a capital A. Yeah, capital A. That's number 3 on your homework. Let's try another one. Let's try number 4, the microwave problem. Get rid of this. Okay, number 4 is the current in a microwave oven is 6.5 amps. If the resistance of the oven's circuitry is 19.2 ohms, what is the voltage? Yeah, let's check. So we're going to solve for voltage, right? We want voltage, so we're going to have current times resistance. So we have volts equal current times resistance. We're just going to plug things in. Our current is 6.25 amps. We're going to multiply that by 19.2 ohms. Yeah. To get our voltage. So voltage is calculator time. 6.25 times 19.2, 120 volts. Pretty straightforward, right? Let me double check, make sure there's nothing in there. I think that's all we really need. Let's look at this other type of problem. Sorry, I paused for a while there. So we also have problems that look like this. We have V, I, and R. Then it gives us a space there. This one says 3 amps, and this one is 5 ohms. Oh, we'll fix that, don't worry, it's good enough. All we're doing is finding the missing piece here, right? So we're going to our triangle. We're looking for volts, so we have current times resistance, so we have 3 times 5, making it 15. 15 volts. I think that's all we need then. that should be about all we really need.